Welcome to IMSc Facets 2023. Thanks for showing up in the morning on a Monday morning. So just a very couple of lines of introduction about IMSc. So IMSc is a research institution with groups in maths, physics, theoretical computer science, and computational biology. And we have integrated PhD and just PhD and integrated PhD programs. So you will hear more about these hopefully in the panel discussion later today. But the program today is kind of centered on maths. So I'm guessing most of you are either interested in maths or pursuing maths programs. So we'll have a total of 3 talks and panel discussion, and all by IMSc members. So so without much ado, we'll just get started with the program. And our first speaker today is Professor Viswanath from the mathematics group in IMSc. So I welcome Viswanath. And I myself am Sushmita. I'll be giving a talk later today.
Hello and good morning. So these sessions are supposed to be, not necessarily lectures per se, but more of an activity-based thing. So I'll probably, along the way, sort of get some of you to come up and do some of the calculations, maybe, for a start. So what I'm going to talk about is something that you've probably seen for a very long time, starting from school at various stages. So there's something called permutations. So maybe someone can give me an example of a permutation. What is a permutation? Or an example? Okay, so if you can just tell me what it looks like when I write it out. So when you say transposition of 1 and 2, you mean 2, 1, and then you want the other 3 in order. Okay, great. So here's 2, 1, 3, 4, 5 was his example of a permutation of 5 numbers, right? And of course, one can do this in all possible ways, and one can do this starting with any number of numbers. Okay, but what I want to start out with is all permutations. So the first question we'd like to look at is, how does one write down all permutations? So let's maybe start a little smaller. So instead of 5 numbers, so let's just look at 3 numbers. So if I had 1, 2, and 3, then how does one write down all permutations? So 1, 3, 2, I could start with a 2 and look at 2, 1, 3, 2, 3, 1, 3, 1, 2, and 3, 2, 1. So here are 6 permutations. Now so it's easy to see I've written all of them, right? Now let's look at the next case. So if I look at 1, 2, 3, and 4, how many different permutations can I have? 24, right? So that's 4 factorial. But the question is, how do we write all of them down? So So let's try to write down all permutations of the numbers 1, 2, 3, and 4. Okay, so let me write out, maybe let me call on some people to come and do this. So I want 2 volunteers who will help me write down all permutations of 1, 2, 3, and 4. One more? Okay, please come up. So you can sort of split the board. Get you another piece of chalk. Okay, so your task is to write down all permutations of 1, 2, 3, and 4 which start with either 1 or 2. Okay, so you would please write everything down which starts with 3 or 4. Yeah, you start only with 1 or 2, correct. Okay, so how many should each of you have? 12 each, I suppose, right? So half of 24. Okay, so let's see. Are you convinced that you got all of them? So let me ask you, did you get all of them? Okay, so you seem to have a certain method of listing them out, right? How have you enumerated? Why did you write them out in this order?
Generally, you start with fixing one of them, and then you switch only the last two. So
Okay.
only for combinations are there for the last ones.
Okay.
Then go to the next one and then same.
Okay, wonderful. So this is what you would call, so I don't know if people sort of noticed or understood what she just said. So you sort of need a systematic way of writing all of them out. So you fix each in turn. So you have 3, 1, 2, 4, and then you continue to fix 3 and 1. You only change the thing at the end, 2 and 4. Then you come one step back, start 3, then 2 and 4, 2, 4, 1, and so on. So this is what you would call alphabetical order, right? Imagine that instead of 1, 2, 3, 4, I had the 4 letters A, B, C, and D. What this list here is just writing all possible, permutations, but in alphabetical order, right? A comes before B, B comes before C, and so on. So your list is not quite in alphabetical order, right? It's semi-random. I see. Okay, great. So. I mean, that's also important in some way. So one often wants to generate, for example, random permutations. So there are ways of doing that. But usually one is interested in ensuring you got everything, right? So if you write it sort of in any order, and it's much harder than it looks, right, to write all of them out, the trouble really is figuring out whether there are any repetitions. So usually you sort of just write them out, and at some point, there's something up in the list which has also been written up again. Right. Okay, great. So thank you very much. So maybe you can just tell me your names.
Avani.
Avni from?
IT Madras.
IT Madras, okay. Abhinandan. Also from IT Madras. Okay, great. Thank you very much. Okay, so let's look at this order here, the alphabetical order that Avni wrote out for us. And now I'm going to do this for 5. So let's imagine writing out all permutations of 1, 2, 3, 4, and 5 in alphabetical order, okay? Or what's sometimes called lexicographic order. So for example, the very first permutation would look like this, of course, 1, 2, 3, 4, 5, right? And what would be the very last permutation? So the 120th, so this is roll number 1, if you wish, in alphabetical order. And roll number 120 would be 5, 4, 3, 2, 1. Okay, so that's the very last guy. Okay, now there used to be a clock here, no? So here's the question. Who's roll number 61? Sort of at the halfway mark. So let's find out the two middle guys. Who's 60 and who's 61? So think about it. Just sort of work this out. Sorry, what? 3, 4? 3, 4, 1, 2, 5, and 3, 2, 5, 4, 1. Yes, absolutely. How did you get there so fast? Okay, great. So let me sort of say what you're saying a little bit more expanded form. So how do we find out, so we have to break this down a little bit, right, in order to, so for example, like we just did, we first look at the permutations which begin with 1. So how many of those are there? They're all going to come first in the list. There are 24 of them, right? Just everything which starts with the 1. So this is 24. And the next set of 24 will start with 2s. So that accounts for 48, right? And then the 2 guys we are looking for, clearly they must start with a 3, right? Because roll number 48 was the last guy with the 2s. And 49 to 72 will all start with 3s. So the ones we are looking for are certainly within the 3s, that we know, right? But then within the 3s, we need a sort of a finer way of figuring out where, who is where. So how do we do that? Well, this is a set of 24, which you can really think of as permutations in which the first guy is a 3 and the remaining 4 are just all possible ways of writing 1, 2, 4, and 5. Right? It's all possible permutations of 4 numbers, except the 4 numbers are 1, 2, 4, and 5 instead of 1, 2, 3, and 4. Okay, and so there are 24 permutations, but again, in those, you look at how many will start with a 1, right? So this is sort of what this alphabetical order entails. So I start with a 1, there will be 6 permutations which start with 3, 1. So the first 6 from 49 to 54 will all start with 3, 1. Okay, and then the next set, which is from 55 to 60, this collection will start with a 3, 2. Okay, and this we are asking for who is number 60. So it is the 6th guy in that list. It's the last one. So the first 2 are 3 and 2, and what's the very last of permutations of 5, 4, and 1? Well, you write them in descending order, right? 5, 4, 1 will be the last of the 6. Okay, so you're done. Then 61 is the next set of 6. So if you look at this guy, it's going to start, 3, 1 is done, 3, 2 is done, 3, 3 is not possible, 3, 4. This is the next. The first 2 digits are 3 and 4. And then it's the first number in that set of 6. It's the first permutation in that set of 6. And that permutation is just obtained by writing 1, 2, and 5 in ascending order. Right? So in a sense, what we are really doing is sort of taking this collection of 120 and sort of dividing them up into groups of, first of 24, and then within the 24 into groups of 6. And if you had to keep going further within 6, you could look at groups of 2 and so on and so forth. Okay. Okay. So this is sort of one of the things one often wants to do, which is you imagine that I've got all permutations of 1 to n, and I know that I n factorial them. I arrange them in alphabetical order, and often I want to know what is the 100th element of that list in alphabetical order. Okay, and in a sense, what we have here is a systematic way of finding that out. Correct.
It has to be 3.
Correct.
Then it has to be the lowest because they're the middle 2.
Right.
It has to be the lowest pair, which are closer. And since now we have strictly ordered them, it has to be other things.
Correct. In either in descending order or ascending order. Correct. So this is certainly special for this, but.
So in the middle half, this will work in general.
Correct. Correct. Absolutely. But what I'm suggesting is that this actually works in general. If I just take any number n, right, and I look at permutations of 1 to n, and then I ask for what is the kth number in that list, kth permutation in that list in alphabetical order, you can just determine it just by using k.
Yeah, so what I was thinking is, for the middle half, it's even special that we don't need to do this procedure, we can just determine it.
Ah, that's what he's saying. Okay, it's faster, it's easier is what he's saying. Sorry, yes.
We can just directly always
Write down what it is. Okay, fine. Sounds good. Okay. But let me ask you another question. So, I take an element, so 2, 5, 1, 3, 4, for example. So here's a permutation. So I don't know, it occurs somewhere in the list. We can find out where it occurs if we needed to, but I'm not going to worry about that. Okay, this fellow is roll number something, K. So here's my question, who's roll number K plus 24? If I tell you that this permutation is it occurs somewhere in the list, what's the permutation which is 24 places after it? Why? Why? Mm-hmm. It is what do you mean by a shift? So this occurs in some, we sort of know in which batch of 24 it occurs. It begins with the 2. So this list will occur between roll numbers 25 and 48. Right? And then I have to go to the next batch of 24, which is the ones which begin with the 3. But,
the index is the same.
Right.
In this batch of 24,
Everything starts with a 3. So the first guy is a 3. But what do I know about the other 4?
Now they are the same order as 5 and 2, 4.
Okay.
And 5 and 3, 4 have the same order.
Wonderful. Right? So if you sort of see how this alphabetical order works, what are you doing? This 2, you're changing to a 3 because that's in the next batch of 24. Okay? And then the remaining 4 numbers here are 5, 1, 3, and 4. Right? And those you are writing in a certain order. So when I say 5, 1, 3, 4, there are only 4 of them. So let's just say 1 is the least, 1 is the smallest, 3 is the next smallest, 4 is the next smallest, and 5 is the next smallest. So I sort of arrange them in this order. Small, medium, more medium, large. Okay? Or if you read it the other way, largest, smallest, first medium, second medium. Right? Now I do the same thing to whatever, right? It's the 4 numbers that are left over here must be arranged in the same relative order. This is how you would call it. It's in the same relative order as these 4 numbers. Okay, so now here the numbers I have are 1, 2, 4, and 5. So how should I arrange them so that they have the same sort of order as this? The largest number should come first. So out of these 4, 5 is the largest. I put it first. 1 is the smallest. Here again 1 is the smallest. This is sort of the first medium guy, which is a 2. And this is the second medium, which is a 4. Is this all right? This notion of relative order. So the first number I fix, it must, from 2 I change it to a 3. And then among the remaining 4, there is a certain relative ordering. The tallest guy comes first, the next tallest, whatever. I've done whatever it is, 5, 1, 3, 4. I now arrange these in the same relative order. Except I'm left with some 4 other numbers because the first entry is now a 3 instead of a 2. Okay? So that's what my 24th guy from that stage onwards looks. Okay, but if you stare at it hard, what have I done? What's really happened going from here to here? Perfect. So all you have done is just swap 2 and 3. 2 and 3 have now become 3 and 2. Okay? So when I go 24 places later, all I do is just swap 2 and 3. Okay? It's an interesting observation that's all really happens at the end of this. Right? The logic we gave is maybe how you want to think about it. Okay. Now, what do you think is the general principle? So if I wrote something else, 4, 5, 3, 1, 2, what's 24 places after this? What? Why do you change 4 and 5?
Because the same logic applies. When you have to change from if I is the leading digit, then I plus 1.
Okay. So you have to look at what the leading digit is. That's exactly the thing. So the 4, which is the leading digit here, must become a 5. Okay, and correspondingly the 5 will become a 4. Okay, so it's an interesting thing that the fellow who's 24 places after any given permutation is just obtained by swapping the number I, which is the leading digit, and I plus 1. Okay, you just interchange the roles of I and I plus 1, you'll get the fellow who's 24 places after you. Okay. Who comes 48 places after? We give you a permutation and ask you, which is the guy which is 48 places after this? So I swap 2 with the 3. To go 24 more steps, I can swap the 3 with the 4, right? And if you sort of see what that entails, it's sort of a two-step process. I mean, you can think of it like that, or you can reason the same way as we did earlier. If you're going 48 steps, that means the 2 must become a 4, and the remaining 4 must be maintained in the same relative order. Okay? If you do that, you will see it's just the same thing as first swapping 2 and 3, and then swapping 3 and 4. Okay, so I don't want to get into this too much maybe, but there is something called the factorial base of numeration. So the usual base of numeration is, decimal or binary and so on, right? So given a number, you express it in powers of sums of powers of 10, that's what the decimal expansion is. Or if you do it in powers of 2, it's binary, right? So more generally, you can actually try to write a number as a sum of factorials. Okay, so let me tell you what I mean by that. So if you look at, maybe we should take some simpler example before I get to 60. So let's see. So if I wanted to write a number in binary, for instance, binary is okay. Yeah. So if I wrote 9 in binary, I suppose it is. What is 9 in binary? Wow, you guys are really quick. 1, 0, 0, 1. Oh, that's 8 plus 1. Okay. So it's 2 cube plus 2 to the 0, right? So it's 1 times 2 cube plus 0 times 2 square, 0 times 2, and then 1 times 2 powers. So that's 9 in binary. Okay. Likewise, we will. So what's the important property? So if I did this in other bases, let's do something else. Maybe what is 14 in base 3? Do I still use only once? Okay, let's go a bit higher. 16 in base 3. Let's do, that was already 1, 1, 2. Okay, saved. So 14 is 1 times 3 square. That's 9 plus 1 times 3, 12 plus 2 times 1. Right? So what are the digits I use? I use the digits 1, 1, and 2. I mean, the base 3 of 14 is 1, 1, 2. The point here is that the digits involved are all numbers from 0 to the base minus 1, right? So you only use those digits. Okay, now the factorial base of numeration is the following. You try to write this as a sum of factorials. Okay, so let's do this. 60 is 4 factorial, that's 24. But it's 2 times 4 factorial. So my digit here is going to be a 2. Okay, it's 2 times 4 factorial. So that's 48 plus the next factorial involved is 3 factorial, 6. So it's 2 times 3 factorial. Is that right? 48. So I'm already at 60, right? Okay. So that's my, maybe we'll do 61. So that's plus a 1 factorial. Okay, I guess I'm doing all right. So it's 1 times a 1 factorial. Okay, now what is this? I mean, what am I trying to do here? So imagine, just like we did binary or ternary, the factorial base of numeration is like the following. It's as if the place values are the various factorials. Okay, so imagine 1 factorial is sort of a units place, 2 factorial, 3 factorial, 4 factorial are sort of your various place values. Okay, so let's just do this it's not quite a base of numeration. It's not powers as we have in the usual decimal or binary, ternary, and so on. This is, imagine let's just do this for fun. Okay, so I make my factorials as base of numeration, but then what digits am I going to allow? So for example, so I have this guy 2 factorial. Let's say I allowed the digit 3 here. Okay, but then 3 times 2 factorial becomes 3 factorial, right? So if I allowed the number 3 here, then I would also be able to write this number, which is 3 factorial, as, so imagine this number 0300 in the factorial base would also be the number 0100, because it's 1 times 3 factorial. Is it okay? So for now, to summarize, I'm sort of inventing this crazy way of writing numbers using place values as factorials, and I'm trying to figure out what digits am I allowed to use, right? By using the same logic as we use for binary, ternary, and so on. What digits would make sense? So for example, here if I allow 3, then I'm in trouble, because this will sort of have 2 different expressions. So the factorial base essentially says I'm only allowed to use numbers from 0 to 1 in the units place. So this can be either 0 or 1. This fellow can either be 0, 1, or 2. This fellow can be 0, 1, 2, or 3, and so on. Okay, so it's strange in that sense as well. What you allow in each place actually is different, right? Unlike the usual basis of numeration where you allow the same sets of digits everywhere. Okay, so let's just check that this would work fine. So if I actually took the number 111, what would that be in this? Sorry, not 111. What's the largest number I can write? 321. Right? Because the maximum digits I'm allowed are 3, 2, and 1. So if you put those in, what number is this in the factorial base? So it's 3 times 3 factorial plus 2 times 2 factorial plus 1 times 1 factorial. What? Okay, great. So, I mean, without calculating, this should actually be 4 factorial minus 1. It should be 1 less than the number that you can get, the next smallest number. So, because 4 factorial, I would be able to write as 1000. Right? So, it's a great exercise to do this. So, this is the factorial base of numeration. Just start writing out all the numbers like you do binary, ternary, and so on. Write out the factorial expansions of each of the numbers. You'll find it's very interesting. Okay, so why would somebody want to invent something crazy like this? The answer is that it's actually got something to do with trying to figure out the lexicographic, the roll number of a given permutation. Right, okay. So if you sort of observe what we did, so what does a factorial base actually do? For 61, for instance, it tells you that 61, the roll, so this allows you to answer the following question: who is roll number 61 in the list of all permutations of 1 through 5? Okay, so what this tells you is that when you scan the whole list, you will first run through 2 batches of 24s. So the first 2 batches of 24s are gone. Right? That accounts for this. So you're already in permutations whose starting digit is 3. Right? 2 batches of 24 is gone. So this fellow starts with a 3. Okay. Out of that, 2 batches of 6 are also done. I have to first travel through 2 batches of 24 and then traverse through 2 batches of 6. Okay. So what does that mean? The first batch of 6 would have started with the number 1. The next batch of 6 would start with the number 2. Okay, and so now I'm in the next, even beyond that, I'm in the next further batch, which will start with the number 4, right, because 3 is gone. So I sort of know what the next number looks like. And then I look at this, and that tells me where I am, and so on. Okay, so I'm not going to do this in full, but this is something for you to think about and work on at home. So if I want to figure out, a certain roll number, given a number k, I want to figure out what is that particular permutation in lexicographic ordering. What I do is I first express that number in the factorial base of numeration. And in a sense, secretly, what it's implementing is what we just did, trying to figure out batches of various factorials. Okay, great. So that's something for you guys to think about a little bit more at home. Now, let me ask for, what are pictorial ways in which you think about permutations? So if I say a permutation and ask for a picture, cycle, okay. Any other? So he said cycle, that's one way of thinking about permutation. But I'm asking for a picture really. Okay, oh, you are thinking about a cycle drawn as a picture. Okay, great, yes, absolutely. Okay, any other ways of pictorially depicting a permutation? Yep. Okay, great. So let's write that same permutation 2, 5, 1, 3, 4. I can just think of it as a function. So what does that mean? So these are the 5 positions. So in the first place I have 2, second place I have this, and so on. So I'm writing down the positions or place, I don't know what to call it, positions. 5 positions, and these are the values in those positions. So I can think of it as a function from positions to values and depict it like this. So it's a function from the set 1, 2, 3, 4, 5 to itself. So on the left are the positions, on the right are the values. So 1 goes to 2, 2 goes to 5, 3 goes to 1, 4 goes to 3, and 5 goes to 4. Oops. 5 goes to 4. Okay, so that's my picture of a permutation. You can also depict it as cycles. You can sort of decompose it into cycles and write that down. Now, so here the way we drew these lines, so this is just a function if you wish, right? All I'm saying is that this fellow goes to that fellow and so on. So in a sense, I'm not thinking of it geometrically. So my lines are all crossing here. They don't mean anything really to cross. So think of it as, this sort of a beam of light I'm shining from 3 to 1. So all these beams of light are sort of crisscrossing each other. Now, this picture is something that you can, make a little different, and that's something which Sushmita will probably talk about later this afternoon. This is sort of the classic thing that one does in math, just to sort of see if you can generalize that same notion a little bit differently. So what if instead of beams of light, you thought of them as, say, threads, for instance, or strings? You actually had strings connecting these numbers. So take a function, but now just imagine you're putting strings which connect each position to its value. The only new thing that happens is that strings can, they can go either under or above each other. So that's something that Sushmita will talk about a little bit more. But so this is my picture number 1. I can draw another picture, which is to think of them as cycles, which is 1 goes to 2, goes to 5, goes to, so I say 1 goes to 2, goes to 5, goes to 4. So in this case, it's all just one cycle. It looks like 3 back to 1. So this is another picture of the same permutation, just a single cycle. And yet another thing you can do is to draw the graph, right? I mean, just of the function in some sense. So 1 maps to 2, what happens? 2 goes to 5, 3 goes to 1, 3, 4. Right? So something like that. So I can sort of think of it as something which keeps going up and down. Okay, so that's my sort of 3 different ways of thinking of pictures or permutations in terms of pictures. Now let me get to the title of my talk in some sense, which is pattern avoidance. Okay, so we'll talk about patterns. Now what is a pattern? So pattern avoidance in permutations. So this is a property of permutations. So let's do it sort of in a very special example. So I'll define what I mean by pattern avoidance. So a permutation of the numbers 1 through n, permutation of numbers 1 to n is said to contain a pattern. And I'll take a very special pattern. It's called the pattern 2, 3, 1. So I say that a permutation contains the pattern 2, 3, 1 if something happens, if and for this really this picture of permutations is probably what's best. So what does it mean for a permutation to contain 2, 3, 1? So here's a picture of the permutation. So 2, 3, and 1 I think of as three numbers. 1 is the smallest, 3 is the largest, and this fellow is medium. So so I have three numbers: medium, large, and small. Now what this says is that when I write out my permutation, then I should be able to find some three numbers which occur in that same relative order. That is, I find the medium guy coming first, then the large fellow occurs, and then the small fellow occurs. Okay, some three out of the n numbers. So let's see this picture which I drew. So what is this permutation? 2, 5, 1, 3, 4. Okay, I'll complete my definition in a minute, but let's just look at this example. So I'll take the permutation 2, 5, 1, 3, 4, whose graph I drew. I want to know when I scan it from left to right, not necessarily consecutively, right? Can I find three numbers such that medium, large, and small occur in that sequence? For example, these three, right? 2, 5, and 1. 2 is sort of the medium of these three. That occurs first, the large comes next, and then the small comes. Right? So this is actually consecutively. Let's see if can you see things which are maybe non-consecutive like that? Not really, nothing else, I suppose. So, but here is certainly a sequence where they occur one after the other. So let's do another example where it's maybe somewhat farther away. Okay, so here's another example. So I can have the medium guy, which is 2. So look at this fellow, 2, 3, 4, 1, 5. In this permutation, I can look at these three elements, 2, 4, and 1. They don't occur in sequence, but of these three, this fellow is the medium, this is large, and this is small. Okay, and sometimes you will find more than one like that also. So here, for example, I can also take these three fellows, 2, 3, and 1. Right? 2 is medium, 3 is large, and 1 is the smallest of the three. Okay? So is the definition clear from the examples? I should look at my permutation, scan it from left to right, find some three fellows such that of those three, the medium guy comes first, the large comes next, and the small comes after that. Okay, so that's really this sort of picture, medium, large, small. So you will find some three dots, not necessarily consecutive, which are like this. Okay, so let me write it out. Formal definition is sort of boring, but it says it contains this pattern if there exists three indices So first I need to write something, a permutation, let's call it A1, A2, AN. So I'm writing this permutation, the n numbers occurring in the permutation as A1, A2, AN. And I should be able to find 3 indices I, j, k with I less than j less than k such that AI is the medium fellow. So AI comes in the middle, AJ is the largest, and AK is the smallest. Okay, so that's just a formal way of writing the same definition. Okay, so this is called permutations which contain this pattern. So I'm only doing this for this special pattern for now, and we will come back to the more general thing in a little bit. And however, I talked about something called avoidance. So if a permutation does not contain the pattern 2, 3, 1, then we say it avoids the pattern. Okay, so avoiding the pattern means you should not be able to find any such triple which are in this relative order. Okay, so if a permutation does not contain this pattern 2, 3, 1, we say that it avoids 2, 3, 1. Okay, so that's what pattern avoidance means. Okay, so why does one want to study things like pattern avoidance? What's this really got to do with permutations? Now that's got a little to do with how one sorts permutations. So if I give you 2 permutations, how would you determine if one is more permuted than the other? Right, I write 2 sequences of numbers 1 to n. When would you say one of them is more permuted or more mixed than the other? How would you measure? What's the measure of being more permuted? Okay, how many times it breaks that cycle? Okay, meaning how many pairs of numbers are out of order in some sense. That's what you mean, right? Okay. Another way of rephrasing what you just said is we can measure it by the amount of effort it takes us to sort it back into correct order. Okay, how many exchanges I need to do in order to sort of bring it back into the correct order. Okay, so that's a measure of how permuted something is. So this is what we call sorting, right? So how do you sort a number? So here's 2, 5, 4, 3, 1. What does it mean to sort? So when we have algorithms to sort this back into usual order, one of the possible things is the following. We sort of make several passes of this sequence. So we start from the left, go to the right. So as I move along, I find that these 2 fellows are out of order. So I bring them into order. I only do exchanges of consecutive out of order pairs. So this becomes 2, 4, 5, 3, 1. Okay, so I brought this into order. Then I sort of look at the next pair, and they're out of order. So I swap again. I have 3, 5. 5 is again out of order. So I swap it, I get 1, 5. So I had to do sort of 3 swaps in the first pass. And at the end of this process, observe 5 is in its correct place. And then I again start from the left. I sort of again go through. 2 and 4 are okay. 4, 3 are out of order. 4, 1 are out of order. Okay, I again go through. 2, 3 is okay, but 3, 1 is out of order. I again go through. 1, 2 is out of order. So I firstly had to make sort of 5 passes of this string from left to right. And what I can do is I can count at the end how many times I exchanged 2 numbers, the number of swaps required. And that's a measure of how permuted my original permutation was. So for instance, if your permutation was 1, 2, 3, 4, 5, the thing that's actually in order, how many swaps would you make? 0. You would never ever end up having to make a swap, right? You would make passes, but not a swap. If it's out of order, 5, 4, 3, 2, 1, how many swaps would you make? n, 5 in this case? 5? 10 you said, sorry, right. Okay, so the very first time you would make 4 swaps. The next time 3, 2 and 1. So 4 plus 3 plus 2 plus 1 is just 10. So you actually need 10 swaps to bring that into order. Okay, so that's the most permuted permutation. Okay, so of course there are, this particular algorithm I talked about is, one of the standard sorting algorithms. I don't know, bubble sort, or it's called bubble sort. Okay, so there are exchange sort and bubble sort and so on, which essentially do variants of this. But I want to talk about something slightly different. So let's do something else, and this guy is called stack sort. Okay, so stack sort is the following. I don't allow myself this multiple pass algorithm. I'm not allowed to go through it again and again and swap things, bring them in order and so on. Instead, I have a very restricted machine. Okay, so all I have access to is the following. So imagine I've got 3, 1, 2, 5, 4, and I want to swap this into order. Okay, that's my goal. But all I have is the following. I've got a railway track. Okay, into which, so imagine there are sort of bogies of a train which can sort of be brought into this railway track. So this is the end of the track. And I've got another railway track. These sort of intersect here. So I have 2 tracks. So I can sort of push my bogies in, and I can park them here, one on top. And then I can pull the topmost guy out of this into this other output stream. Okay, so that's my output is finally going to land up there. So this is all I have. I only have access to 2 railway tracks of this in this configuration. Just using this, I want to sort. This kind of sorting is called stack sort. Okay, so let's do an example. It'll become clear enough what I mean. So first, I push the 3 into the track. So the 3, bogie number 3 sort of goes and parks itself there. Okay, what do I do next? Very little I can do. There's 1, so I push 1 into the thing. But remember, that's where my output is finally going to live, right? And I want to sort this into correct order. So how will I achieve that at this point? Push the 1 out, right? I'm allowed to do that. So I, what's called pop in this usual terminology. So I pop the 1 out. So bogie number 1 went to its correct place. Now let's see, 2, push, 2 park there, and now pop 2 out. Okay, now pop 3 out. I can do that. Next, push 5 in, push 4 in, pop 4 out, and then pop 5 out. Okay, it's fine. So this particular machine is what we'll call a stack. Okay, so all I have is access to a stack, and I want to try and sort my permutation just using my stack. Okay, good. So we just now did this. So let's do another one. Tell me, sorry, who asked the question? Okay, so let's do that. So I have 1, 2, 4, 5, 3. Yes? So what will happen? Okay, so 1 goes in, goes back out. 2 goes in and goes back out. 4 goes in and parked. 5 goes in as well. 3 goes in, and then 3 goes out. No, you're not allowed to do that. that track cannot take things back. I mean, this is only the, I can only push things. This is a one-way track, can only move like this. Okay, so I'm not allowed to put things back into this. If I can do that, of course I can, I can pretty much sort everything. So, okay, excellent. So what's your conclusion? You cannot? Okay, you cannot sort this guy using a stack. Okay, so that fellow is a stack sortable permutation. This is something that I could sort using a stack. This is a non-stack sortable permutation. So, see, I'm tying my hands behind my back, right? I'm only allowing myself to use a stack. Earlier, I was allowing myself to do multiple passes of my string and exchange and do all kinds of stuff. Here, I'm not doing that. So the stack seemingly is a powerful machine, but it's not powerful enough to sort all permutations. Okay, great. So all my punchlines are being, thank you, yes. So why couldn't I sort? So let's just analyze this point. Why were you unable to do this? What happened? What went wrong? So the 3 went in, right? So let's just analyze what happened the one previous step. So 3 went in, and now it's time for the 3 to go out. Okay? At that point, what happened? Why did it fail? I mean, how would you describe in words why this failed? It is not in? Okay, the parking was not in lexicographic order. Let's try and say it like this. So I have the 3 which will go out, and the next guy which needs to go out, which is the 4, is stuck below a larger number, right? So the 4 is sort of stuck below in the stack. The fellow above it, which I can remove, is actually bigger than 4. So that will have to come out first before 4 comes out, right? So the problem is 4 got stuck under a bigger number, okay? Now when will this happen? Why did this happen? Because when you looked at these 3 numbers here, this fellow was the smallest number, 4 is the medium, and this guy is the largest. Sorry, the other. The 3 is at the end. 4, 5, 3. This was medium, this was large, this was small. So when they moved into the stack, the medium guy is sort of parked at the bottom, the larger guy is above it, and the smallest guy is here. Right? So when they come out, the smallest guy is supposed to come out first, as it will. But then after the small, at some point, the medium will have to come out, right? But it's stuck below the large guy. So when I pull things out, the medium fellow will not be able to exit before the large guy exits. All right? Okay, great. Now, this is sort of one, maybe where it first came from, this whole notion of stack sortable permutations, and rather the whole notion of a 2-3-1 avoiding permutation. So observe that this permutation contains 2-3-1. So let's write out what we have observed. So let me call it a theorem, is that a permutation is stack sortable if and only if it avoids 2-3-1. Okay, I mean, I didn't prove this. I guess what we have said so far is only seeming to suggest it, but it's not too hard to prove. Okay, so at least we have seen one direction. If it contains 2-3-1, it's not stack sortable, right? This thing will happen if it contains 2-3-1. So at least one direction we have seen, but you can also prove the other one. Okay, great. So let's ask ourselves in light of this theorem. Okay, this is what stack sortable is. How many stack sortable permutations are there? Total number of permutations is n factorial, right? Sorry, what? Why? Okay, so what is push? What do you mean by push and pop sequences? Okay. Okay. Okay, great. Absolutely. Wonderful, understood. So let me state what you're just saying a little bit more in more detail. So what is the operation of a machine? So let's encode the stack in the following way. So let's do it to this guy that we started out with. As the stack moves, so this was what, 25431, right? Sorry, is that right? No. क्या था? 31254. Sorry, thanks. 31254. Okay, so I'm going to do this. This one, and maybe someone can come up and do the next one. So I'm going to encode the working of the stack in the following manner. So what can I do at every step? Stack, there are only two things I can do. I can either push or pop. Push means move things from this track into the parking area. Pop means move it out of the parking area into the output track. Right? There are only two things I can do. So at every step, I will just keep track of what I'm doing. So the very first step, the 3 goes in, right? So the 3 is a push. So I will encode it as, say, zeros and ones. So if it goes in, I'll put a 1. Okay, the push operation is a 1. So 3 went in there. Next, 1 goes in there. It's also a push. Okay, so 1 is push. That's my encoding. And 0 will be pop. So I had to do 2 pushes. And now what's next? 1 popped out. So that's a 0. So 1 pops out. Now I've got a 2, which I push in, but also pop out, right? So the 2 has to be pushed in and then popped out. And now 5 pushed in. Sorry, no. I have to pop the 3 out first. So 3 is a pop. Okay, now 5 and 4 are both pushes, and then 2 pops. Is okay? So all we did here is to encode the operation of the machine, what it was doing at every step. Okay? Now, if I give you this, then you can also figure out what the original thing looked like. Okay. So can I ask for 2 other volunteers? Two more people write down push and pop sequences for me. No, I'm not asking you. One more person? Yes, please. So I'm just going to write down. So I have 4, 2, 1, 3, 5, and I want you to write the push and the pop sequence for it. And I'll sort of give you the reverse problem. So if I have let's see, 1, 1, 0, 1, 0. 5. Do we have all of them? Sorry. Just give me a second. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Yeah, I think it's all right. So find what the permutation looks like. Okay. 4, 2, 1, 3, 5. That's what I was trying to count. Am I off by something? 1, 2, 3, 4, 5. 1, 2, 3, 4. Oh, I have 6. Okay, sorry. That be all right? No. Sorry.
I think it's fine. It's 5 zeros, 5 zeros.
There are 5 zeros and 5 ones. No, but then I have 2 zeros again. Okay, yeah, fine. It's only good, you're saying. Okay. Yeah. So let's see. 4, 2, 1, 3, 5. What's your sequence of pushes and pops? You already have it. Okay. Let's see. How did you get this?
First I pushed this one. This
Okay.
one I did 3 pushes.
Okay.
And did 2 pops.
Okay.
And then I pushed this one and popped this one.
Okay.
And then I popped this one.
Okay.
And then pushed in.
Wonderful, wonderful. Okay, good. So, I mean, after a while, you can sort of just see from the numbers what you have to do. You don't actually have to draw the tracks. Okay, wonderful. Thank you. So this is the push-pop sequence which corresponds to this guy. So that's a harder problem, which is, if you're given the push-pop sequence, how do you figure out what the permutation looks like? Okay, wonderful. You should explain to us what you did.
Okay, so whatever the first one is just stayed there. So you know that's not 1. And then the next number that came in, we popped it immediately, so that should have been 1. Then again you did that, so that should have been the next one, which is 2, 3, 4, and then the last one is remaining, which is 2.
Okay, wonderful, great. Okay, so essentially after a while you sort of get the hang of how this pushing and popping and the original permutation, how they're related and so on. Okay, I mean, one can also prove statements about, something more about the pushing, popping and this. But I'm sort of more interested in trying to enumerate, trying to figure out how many permutations there are which avoid 2, 3, 1. Okay, and so the first thing we observe is that that number is the same as the number of push-pop sequences. Okay, so if I can count the number of push-pop sequences, I have managed to count the number of 2, 3, 1 avoiding permutations. Right? You agree? Because these are the same thing we have said. Push-pop and this are really sort of like a bijection. If I give you this, you can find that, and if I give you that, you can find this. Okay, and you can check it's a bijection and so on. So let's try and enumerate the number of 0, 1 sequences which can arise as push-pop sequences. Can any sequence of 0s and 1s be a possible push-pop sequence? I mean, you could see from what I was doing right there. So that's one obvious condition, right? So how many 1s and 0s do I have in this example? 5 each, right? 5 1s and 5 0s. That's one condition. Okay. Now, starts with 1, ends with 0, absolutely, because the very first thing has to be a push. The very last operation has to be a pop for sure. Okay, and there's one other thing which is implicit. Okay, at any point of time, up to any index, meaning you cut this off at any point, the number of 1s must be more than the number of 0s. Right? Why? Because the number of pushes minus the number of pops tells you how many are still parked there, right? And you cannot pop out more than the number you have in the stack, right? So at any point of time, you cut this off anywhere, and you look how many 1s have you seen minus how many 0s you have seen. That should always be positive, the difference. So there are 3 1s, and I only see 1 0. It should be non-negative. So at this point, at this point of the machine, how many numbers are parked in the stack? 2, because there were 3 pushed in and only 1 popped out, right? And so on. Similarly, here I popped 1 more out, still 1 more left in this stack, but now I have added 1 into the stack, popped, and so on. So the number of pushes until any given point must be more than the number of pops. That's the other condition. And this sort of 0, 1 sequence is best represented as a graph again. Okay, and it's the following sort of graph. So let me just draw the one corresponding to this here. So I have 3 1s. So every 1 I will draw as an increasing line segment, a northeast thing which goes diagonally upwards like that. So the 3 1s, 2 0s, okay, and then 1 0, 0 1 0. So this is my path. Okay, so all I have done is just drawn a picture which depicts the 1s and 0s. Okay, 1 means I go up, 0 means I come down, and the condition that I always see more ones than zeros means that this path, what can I say about this path? It always lies above the x-axis. Okay? It will never go below the x-axis because I rise more than I fall at any given point of time. So these are all paths which live completely in the first quadrant. What are the conditions should they have? They can either go up one step or down one step at every point, and they should come back to 0. They should come back and hit the x-axis. Okay, what does that mean that it hits the x-axis finally? That the number of up steps, total number of up steps has to be equal to total number of down steps. Meaning number of ones is equal to number of zeros. Okay, so these sorts of paths are called Dyke paths. Okay, and they come up in many areas of mathematics. And these are the number of Dyke paths. So these are called Dyke paths of length 10 in this case. Okay, so the Dyke paths of any given length. Length is an even number in general. So in this case, n is 5. And one can actually count these guys. The number of Dyke paths is something called the Catalan number. I mean, there's an actual formula for it. In terms of the binomial coefficients. Okay, so this is called the Catalan number. So let's just do it in the example we were interested in. If I take the numbers 1, 2, 3, 4, 5, how many of the 120 possible permutations are stack sortable? Question is clear? How many out of the 120 permutations of 1, 2, 3, 4, 5 can be sorted using a stack? Okay, so let's plug in n equal to 5 into this formula. So observe that this formula counts the number of Dyke paths of length 2n, and this, as I have said, is the same as push-pop sequences, right? Another way of depicting them. And push-pop sequences are in bijection with stack sortable permutations or 2, 3, 1 avoiding permutations. So let's plug in the numbers. Put n equals 5. That's 1 by 5 plus 1, 6. 10 choose 5. So 10 choose 5 is 10, 9, 8, 7, 6. 6 into 5 factorial. So that's really 6 factorial. $42, you say? Sorry, what? 10 into 9 into 8 is 6 factorial. Okay, great. Okay, so that's 7 into 6, absolutely, correct. Okay, so 10, 9, 8 is 720, absolutely. So that's exactly 42 paths. So out of the 120 paths, 42 of them, out of the 120 permutations, 42 of them are stack sortable. Okay, so this is about 2, 3, 1 avoiding permutations. Now the question is why 2, 3, 1? Meaning why did I only restrict myself to that? Well, because for now, because they are the ones which arise as stack sortability. But having done this, we can generalize the notion to anything, right? So for example, let's make our definition more general. How would you define a 2, 1, 3 avoiding permutation? So 2, 3, 1 avoiding we just talked about. Let's get more ambitious. What is a 2, 1, 3 avoiding permutation? How would you define it? So a permutation is said to contain 2, 1, 3 if what? There are 3 indices, I less than j less than k, such that the fellow which lives at position I is the medium guy, the fellow at j is the smallest, and the fellow at k is the largest. Okay, so let's write it out. If there exists I, so permutation a1, a2, an, AI is the middle fellow, AJ is the smallest, K is the biggest. Likewise, 2, 3, 1 avoiding permutation, 3, 1, 2 avoiding permutation, or 3, 2, 1, or 1, 2, 3, or 3, 2, 1. Pretty much any, take all 6 permutations of 1, 2, and 3. For each of them, you have a class of whatever, sigma avoiding permutations, where sigma is any one of those 6 possibilities. Okay? Okay, great. So let's ask ourselves, now that we have defined one more guy, how many are there which do this? How many 2, 1, 3 avoiding permutations, or 3, 1, 2 avoiding permutations, or whatever else can we find? So let's record what we have so far at least. Number of 2, 3, 1 avoiders is the Catalan number. Okay. So now let's ask how many, I don't know, the other guys. So let me take 1, 3, 2 avoiding permutations. Okay, just the reverse of same, meaning?
Just the reverse. Can you do given avoiding permutation, you can reverse and it will stay 1, 3, 2 avoiding similarly.
Okay, great, absolutely. So observe 1, 3, 2, right? So why did I pick 1, 3, 2 out of all the other possibilities? I know the answer to this. I know that the number of permutations which don't contain 2, 3, 1, I know the answer, how many there are. Okay, now let's look at 1, 3, 2. So what does 1, 3, 2 avoiding mean, or 1, 3, 2 containing mean? It means when I write my permutation, there are some 3 fellows such that the smallest guy is here, the largest guy comes after it, and the medium guy comes after it. Right? There could be many more. So here's my permutation. This fellow, such a permutation is said to contain 1, 3, 2. Right? This is when I say my permutation contains 1, 3, 2. Correct? It's got small, large, medium. But I can now do the following. I can read my permutation in reverse. It's a different permutation, doesn't matter. But I have the following operation. Given a permutation, I can form another permutation from it by just reading it in reverse. Okay? Now if I do that, what happens? So, maybe this is some permutation of 8 or 9, whatever. So I don't know, what is this? Let's just put some numbers. So small is 2, medium, large is 7, medium is 3. Okay, and then I'll put the other numbers appropriately. 1, 2, 3, 4, 5, 10. Oh, okay. So 10, 6, 2, 1, 7, 5, 4. Okay, so here's my permutation of 10. In which I see a small, large, medium, right? But now I just read the same permutation in reverse. So I read it as 8, 9, 10, 4, 3, 5, 7, 1, 2, 6, right? Now in this permutation, what pattern am I guaranteed to see? So let's look at the same 3 positions. Look at the 3, the 7, and the 2. Okay, so when I go from right to left, I see 3 first, then 7, then 2. Okay, what is the relative order of these 3 fellows? 3 is medium, 7 is large, and 2 is small. The same thing, but now the order in which I say it is medium, large, small, right? I don't see it as small, large, medium. I encounter them in this order, medium, large, small. And what pattern is that? Medium, large, small is exactly this. 2, 3, 1, right? Medium, large, small. So if a permutation contains 1, 3, 2, then its reverse contains 2, 3, 1. Okay? So in fact, if a permutation avoids 1, 3, 2, its reverse avoids 2, 3, 1. So this is the usual sort of thing about bijections. So here's what we do. We look at the set of all permutations of 1 to n. To the set of all permutations of 1 to n. I've got this map called reverse. Given a permutation sigma, I just read it in reverse. Sigma going to sigma reverse. Right? Now what I'm saying is that if sigma contains 1, 3, 2, if and only if sigma reverse contains 2, 3, 1. So how many 1, 3, 2 avoiders will I have? Exactly the same as 2, 3, 1 avoiders. That's known to be the Catalan number. Okay? Let's do the other ones. What about 3, 1, 2 avoiders? Okay. Now, look at these numbers. I've got these 10 numbers. So what is it that we need? See, 1, 3, 2 and 3, 1, 2. So I claim I can actually get this fellow from here. Right? How? This is what? Small, large, medium. This is large, small, medium. Right? The pattern is reverse. Instead of first seeing the small guy, then the large guy, I should see the large guy first and then the small guy. How can I engineer it so that that will happen? Okay? So what we'll do is we'll just take this permutation, but change the roles of 1 and 10. Wherever I see 1, I will write 10. Where I see 2, I will write 9, and so on. Okay? I sort of swap the ends. So what does that swapping of the ends do? This will do the following. So 6, 2, 1, 7, blah, blah, blah. Let's write out 3, 4, 5, 6, 7, 8, 9, 10. So let me write out the 3 numbers I care about. Small is 2. If I swap it, what's its partner? 2 goes to 9, right? The second fellow from the right. 7 should go to the 7th from the right, which is what? That's a 4. 3 will go to an 8. Right? And of course, I'll write out what the others look like also. But just focus on these 3. I have 9, 4, and 8. Right? Now, in what order do I encounter them when I see them from this direction? Instead of seeing the smallest first, I will see the largest first. And then, instead of the largest, I will see the smallest. And the medium will remain the medium. Right? Because when I do the swap, all that happens is small and large get interchanged. Okay? So, in fact, not just is there a bijection called sigma rev, there's another bijection called, I don't know what to call it, sigma swap ends. Okay, here's a second bijection, and this fellow has the property that if sigma contains something, if sigma contains 1, 3, 2, the swap end contains 3, 1, 2. Okay? So again, the number of 3, 1, 2 avoiders is equal to the number of 1, 3, 2 avoiders, which is the Catalan number. And one more guy left, which is actually 3 more guys left, but let's do this guy. Number of, what's that? 2, 3, 1, in which I change large and medium. Right? 2 and 3 avoiders. How do I get them? I take 2, 3, 1 and I apply sigma swap ends. So if something contains 2, 3, 1, the swapped guy will contain 2 and 3. Okay? So all these 4 are the same. So here's a very, very interesting fact that the number of permutations which avoid 2, 3, 1 or 2 and 3 or 1, 3, I mean not or, sorry. The number of permutations which avoid 2, 3, 1 is equal to the number of permutations which avoids 2 and 3 is equal to this and equal to this. All 4 are equal to the Catalan number. Okay, I should ask a question at this point. What's the obvious question? What? There are still 2 more guys left, which I didn't say anything about. Absolutely. There is 1, 2, 3 and 3 to 1. So that's the question you should ask at this point. What about the other 2 guys? Right? What can I say about the number of permutations which avoid 1, 2, 3, and the number of permutations which avoid 3 to 1. At this point, I can't say anything about, I can't get them from the other 4. See, those 4 turned out to be nicely related to each other because there were these 2 nice bijections. I could either reverse a permutation or I could swap its ends. And just using them and using that one case which I knew, which is the stack sortable fellows, using that one and these 2 bijections, I got lots of information for free. But then that's my methods are, that's the limit of my methods. I can't apply the same methods to figure out how many there are in these categories. Okay, fine, but can you say something about the relation between these 2 categories? These 2 are at least equal to each other. That we can say. Why? Okay, or swap ends. You can do either of them. Okay, it turns out that here reversing 1, 2, 3 will give you 3 to 1. If you swap ends also, you will get 3 to 1. So in this case, both bijections will actually give you the same thing. So what do we know? These 2 are both equal to each other. Okay, at least that much we know, right? But how many are there? What's your guess? Any guesses? Sum of all avoiders will be? Okay, excellent. I was going to ask that question next. Sum of all avoiders will be n factorial. Is the statement clear? Will it be true? Anybody disagree with this statement? Why not? Right. So how would you do things like that? See, a permutation can avoid more than one pattern, right? Nothing prevents it from avoiding more than one. Inclusion, exclusion, it will be harrowing time, but that's what you have to do, absolutely, if you have to do that. But then you see the trouble is, we don't know how many there are which avoids 2 permutations. We only managed to do this, okay? Okay, great, but that's a great start. That's sort of how we want to think, right? We know all the other cases. How do we do this one missing case? So it's a hugely surprising fact, at least to me, that it is also equal to the Catalan number. But somehow for very different reasons. It's not, philosophically, it's not for the same reason why all the others are equal to the Catalan number. Okay? So that's one thing I wanted to say. One of the proofs of this, so I'm not going to get into this, but let me write this out, something for you guys to look up. Wikipedia itself has a very nice article on this. In fact, most things I've said are maybe Wikipedia is actually the best source to start exploring if you're interested. So if you look at permutation patterns, that's the title of the Wikipedia article. It's a wealth of information. So how does one prove this very last thing? One of the proofs involves a very, very sort of celebrated algorithm in this whole thing called the Robinson-Shenstedt-Knuth algorithm, or the shorthand to the RSK algorithm. So it sort of is something which, or maybe one should call it just Robinson-Shenstedt in this case. It takes a permutation and then sort of generates other combinatorial objects from it. It's called tableau and so on. And that's sort of one way of showing that these avoiders are also equal to this. Okay, a couple of remarks. So 1, 2, 3 avoider is actually a very simple thing. What does it mean to say a permutation avoids 1, 2, 3? It just means you will never find 3 fellows in increasing order, right? I will never be able to see small, medium, large in that order, right? You never encounter 3 numbers in increasing order. Okay, the other final remark that I will make is the following. So the total number of permutations is actually n factorial. Right? Now, as soon as you wanted to avoid one permutation, avoid 2, 3, 1, then the total number falls dramatically, right? Instead of 120, I got 42 in the case of n equals 5. Now, the question in general, instead of n factorial, I've got the Catalan number, right? When I ask it to avoid one permutation. Now, do you know how fast n factorial grows? Okay, it's like roughly like n power n, right? So this is called Stirling's formula, right? It tells you how n factorial grows as n is very large. It's something like n power n. Okay, it's rather large. Now, do you know how fast the Catalan number grows? What does this binomial coefficient look like? It's like more like something to the n. Okay, it's like some constant to the n. So that's sort of what the Catalan number looks like. So in a sense, the full universe of permutations is like n power n. That's how it grows. This is all permutations. This grows like this. But as soon as you impose just this simple criterion, it should avoid this particular pattern. Okay? So pattern avoiders, say let's say 2, 3, 1 avoiders. It's like Catalan number, and if you sort of just expand this out in full, you'll see this is like some constant power n. Okay? So this actually falls dramatically. I mean, C power n is sort of a much smaller rate of growth than n power n, and this itself was actually a subject of a conjecture that was solved not so long ago called the Stanley-Wilf conjecture, which says that, so this probably only solved 20 years ago roughly now, which conjectured that this will always happen, that as soon as you stipulate even a single permutation and ask for how many avoid that permutation, the growth rate of that number will only become some C power n as opposed to the n power n. Okay, good. So maybe I should stop there. Any further questions or comments? Okay, if not,